What attracts you the most in the night sky? An infinite cryptic abyss of darkness, or uncountable multitude of stars there? Yeah, this view is quite impressive, particularly beyond the city, in places with no light pollution. It was widely believed that stars are the main and almost the only elements of the universe structure. In any case, except for stars and a small amount of interstellar gas, astronomers could not study anything. But now we know that the universe is mostly filled with dark energy and dark matter, and stars, gas, and planets make up only a small part of it. According to the diagram, they make up only 0.5% of the universe. Nevertheless, when we look in the sky, we can see nothing but stars. Even a telescope in the sky sees almost nothing except these bright lights. Turns out that, whether we want it or not, we are to study the universe looking at the stars, because there are very few other sources of information. It is the stars that tell us about the evolution of matter, about the evolution of themselves, about the species of the planets, about the biosphere there. The stars themselves are extremely interesting from the physics standpoint. Stars were born in the distant past, and today we find them, for example, in globular clusters. They also appeared in recent past, form nowadays, and apparently will continue emerging for a long time. So, firstly we should figure out where they come from, how they form, and what matter generates those spectacular thermonuclear reactors. Astronomers found out quite a while ago that in the universe except stars there also is rarefied gas. Then dust was spotted. Clouds of gas and dust they called nebulas. Initially those clouds didn't attract the attention of scientists, but with time it felt like we couldn't explain star formation another way. Nature somehow shapes dense objects with high mass exactly from this substance. Let's talk about this process later. Now we have a problem. If this substance steadily transforms to stars, then what matter replenishes it? Where does nebulous material come from? One of its sources could be seen during the solar eclipse. Our Sun is surrounded by corona. If you look closely, it becomes clear that every star constantly loses part of its matter. This stream is called stellar wind, and it is one of the reasons why nebulas exist. But stellar wind is extremely sparse. Nebula mixed from lots of stellar matter lost in this way is not massive enough to create a whole new generation of stars. More intensive gas inflow is needed, and we can observe its source in the moment of star death. And again, we'll talk about it later. For now, it will suffice to know that it is the main source of nebulous creation. Looking at wide-angle picture of our galaxy, you can notice those dark streaks filling the interstellar space. So, in spite of their low density, they can noticeably absorb light. That's why it was challenging for astronomers to look through this dust and examine star formation inside nebulas. But nowadays, with help of infrared radio telescopes, it's not a big problem. At first, astronomers couldn't realize how nebulas could generate anything dense. In the early 20th century, they could observe only thermal and luminous ones, like Orion or Crab Nebula, which were absolutely not appropriate. Because of high temperature, they rapidly expanded. At present, we distinguish three main types of interstellar environment. All of them mostly consist of hydrogen. The one I mentioned before has an extremely high temperature, several thousand Kelvin, and consists of ionized hydrogen. Another one is cooler, so it has atomic hydrogen with electrons in their places. And the third one is made of molecular hydrogen, because of its freezing conditions. So, which type is responsible for star formation? An answer was given by theory, based on works of American astrophysicist James Jeans. He examined the given process. There is a gas environment. Firstly, atoms there have gravitation, therefore they attract each other. Secondly, there is a temperature which intensifies their chaotic movement, and they intend to fly away. The question is what force is going to win. He even came up with a formula which defines it. In short, hot and rarefied gas is not meant to be a star, but cool and dense ones are able to shrink enough. In Jean's time, only hot nebulas could be seen through ordinary optical telescopes. According to his formula, those clouds could create stars with impossibly huge mass. But in 1975, when Jeans and astrophysicists of his generation were gone, scientists discovered the most cold part of environmental gas, molecular one. When they put all needed parameters in James Jeans' formula, they got approximate numbers to the mass of our Sun. And finally we found out what is the birthplace of new star generations. As we already know, stars emerge in cold molecular clouds, and their size is incredible. There are about 5,000 nebulas of this type in Milky Way. An average mass of each one is close to million masses of Sun. You couldn't find such an outstanding object in galaxy, except central black hole or some globular stellar clusters. These are immense space inhabitants, which were hiding from our view for a long time. So how exactly nebulas sculpt stars? There is nothing perfect in our world. Values of pressure and temperature are fluctuating in different spots of gas and dust cloud. Therefore, some colder places with lower pressure are shrinking under surrounding force. This process of gravitational stability makes negligible irregularities of pressure become larger. As a result, individual dense fragments continue compressing and create cores. All that time, the shrinking gas has been releasing its energy in the form of infrared radiation, and temperature was decreasing. This continues up to the moment when core becomes dense enough to be not transparent for infrared rays. So it starts heating up and protostar is being formed. The compression continues, and when temperature reaches 3–4 million degrees, thermonuclear reactions start. Meanwhile, external part of protostar stays cool and rarefied. We can witness that this substance starts spinning around the central star and turns to planets. It is called protoplanetary disk. Here you can see a picture of newborn star HL Tauri, made by telescope ALMA. It also has protoplanetary disk, and we can even notice gaps, which probably implies that planets already formed there and cleared away the space around their orbits. Stars don't tend to appear alone and usually are born close in one short time episode, during from 10 to 12 million years. Yeah, it's not so much comparing to space standards. Area of active star formation are relatively close to us. They are located in Tauri and Orion constellation and researched in detail. But it is difficult to explore distant areas in our galaxy. Our solar system is placed in the galactic disk. This disk is filled with gas and dust substance. It is impossible to absorb whole galactic volume through it. It is better to look at a star formation in neighboring galaxies. Most of them are exposed to us like the open plain. For example, Tarantula Nebula from the Large Magellanic Cloud is one of the largest star occurrence center. Just look at the top of the heaviest stars, most of them are born there. Okay, as we already know, stars appear in big amounts in protostar clouds. And you might have a question: where all of those our Sun's neighbors, and where have all this gas and dust disappeared? This is the work of stars themselves. Firstly, the most massive ones from a group push apart and destroy maternity cloud. Space becomes cleared and only family of newborn stars remains on a spot of gas cloud. But 90% of mass in this area contained exactly in this substance. That means that along with the gas, its gravity also went away. It turns out that now most of stars are almost not linked with anything. Their own attraction is not enough to maintain cohesion of young star group. That's why the fastest ones leave this place behind gas. Remaining ones live together for some time, but they're gradually leaving too. This process is called dissipation or evaporation. It resembles evaporation from fluid surface. Fill a glass with water and leave it in a room. After a week, half is left. After 2 weeks, it is empty. But where have the water molecules gone? After some random collisions, one by one, they accidentally got enough speed to fly out, appear in the volume of the room and never come back. The same thing happens with stars. They interact and push each other with gravitational force. Their speed distribution tends to be sustainable. It is called Maxwellian velocity distribution. With an established Maxwellian distribution, the proportion of stars which move faster than escape velocity is quite slight, less than 1%. But when they leave, the stability of this dissipation becomes disrupted, and star interaction strives to complete high-speed part of a graph. This cycle repeats dozens of times, and cluster loses a significant portion of stars. In the modern era, clusters of small masses containing a small number of bright stars are born in the galaxy. Therefore, their shape doesn't have a clear symmetry. Astronomers call them open clusters. They evaporate quite quickly, so the age of known open clusters is not great, tens and hundreds of millions of years. But there was much more interstellar gas in the distant past in our galaxy. Its clouds were larger and formed much more massive star groups. Some of those have reached our time. They consist of hundreds of thousands or even millions of stars. That's why their shape is quite symmetrical and globular. Globular clusters can exist for billion years, gradually evaporating. You can see such a cluster named Messier 13 located in Hercules constellation. This is one of the most known and scrutinized globular clusters of North Sky Hemisphere. On the photo, it seems like stars there are stuck together, but actually star collision in clusters is a rare event. Main physical parameters in interiors of such stars as our Sun are determined long ago. We know that temperature in the center is 16 million Kelvin and it falls up to 6,000 on a visible surface, that more than half of its mass is centered in the core where thermonuclear reactions take place and generate heat. And moving away from the center, the substance doesn't produce energy, but just transfers it to the surface and releases to space. This data is so examined that astronomers have no doubt about it. But scientists couldn't understand for a while what had been hitting the star. Different sources of star energy were considered in different times. In the early 19th century, there were known only chemical reactions as the source of heat. That's why appeared an idea that the same thing happens inside the Sun. I mean, there was some fuel like carbon or oil which bound with hydrogen like in an ordinary bonfire or oven. It is easy to estimate how long would Sun live if it was the only source of star energy. We all know what happens in the oven and how much energy is released per 1 kilogram of fuel mass. We also know Sun mass and its radiation power, and number of seconds in 1 year. As a result, the age of Sun is close to 6,000 years, which almost matches with the biblical age of our world. This coincidence gladdens scientists. Nevertheless, by mid-century, geologists started to contradict such a small age of the solar system. They estimated how fast sedimentary layers accumulated on seabeds and claimed that Earth is at least hundreds of thousands years old. It was time to speculate how did the Sun warm itself. Chemical reactions weren't suitable anymore. Then they recalled another source of energy, gravitation. Sounds weird, but this assumption is not so unreasonable. Common example, the rock falls down, hits the surface and warms up. Potential energy of mass in gravity field turns into heat. Humanity have been exploiting this energy by different ways for thousands of years. One of them was using the potential energy of water. It falls from dam and rotates the mill or electric generator wheel. Basically, gravity is decent energy source, and Sun is a massive object. The question remains as what could fall on it. Initially, there was an assumption that dust, meteorites and other small stuff fall on the Sun and heat it. But calculations showed that it is not enough for such a colossal energy production. However, in the middle of the 19th century, a great idea came to physicists. Hermann von Helmholtz and William Thomson came up with theory of star compression. Under the influence of gravity, the Sun shrinks while it heats up from the inside and cools down from the surface. Helmholtz calculated that annual 100 meters diameter reduction is enough to generate the heat and luminosity which people can observe. This hypothesis lengthened Sun's life for 30 million years, which conformed with geologists' claims. And eventually people figured out the real age of our planet and the solar system after the discovery of radiation. It turned out that Earth has not millions but billions of years, and again astronomers had a task to enlarge the evolution of the Sun. They firstly thought that interiors of the Sun consist of heavy radioactive elements, and their decay produces heat. But this idea was quickly rejected, and it turned out that not only decay, but also fusion generates heat. These reactions are called thermonuclear. Physicists couldn't understand for a while how exactly these reactions happen. The thing is, fusion is caused by approach of atomic nucleuses, which form more complex element. But two positively charged particles repel each other, and only extremely high speeds can surpass this obstacle. According to calculations, even fusion of the most simple element, hydrogen, requires 1 billion degrees of temperature. There is no such temperature in the depths of the Sun, and again a deadlock. But young Russian physicist Georgy Gamow solved this problem. He discovered the tunneling phenomenon based on a new for this time physics section called quantum mechanics. According to the laws of classical physics, in order to bring two protons close enough that nuclear forces will make them unite, they must be accelerated to overcome the potential barrier of mutual repulsion. But quantum mechanics states that the particle don't have to overcome the barrier, because it can go through the obstacle like through invisible tunnel. This ability exists because particle's position is not determined. It is like blurred in the space. The particle can simultaneously be in different spots and occur in near place no matter what wall hinders it. It is quite a rare event, but in large solar scale it happens regularly. So, thermonuclear reactions commonly have three stages. Firstly, two protons approach each other and unite under nuclear forces. One of them transforms to neutron and releases its positive charge in the form of antiparticle of electron, positron. Also emerges another neutral elementary particle with negligible mass called a neutrino. Now we have an element with the same nuclear charge as hydrogen but with more mass. This isotope of hydrogen is deuterium. When deuterium encounters another hydrogen nucleus, it connects with positron, releases gamma quantum and forms helium-3. When two helium nucleuses fuse, they release two positrons and helium-4 is being formed. Physicists also call it alpha particle. Every stage was happening with high energy release. The presented chain of reactions is the most common but not single. You can see other variations of it on the scheme. But how does this heat reach the star's surface? We know three types of thermal energy transfer: conduction, convection and radiation. Conduction is not so considerable in star interiors, but convection and radiation steadily do this work and displace heat outside from star depths. In stars of moderate temperature, convection is most significant. For instance, we can witness it on Sun's surface in form of granulation. That's how floating hot streams show themselves. Talking about stars, it is also important to mention their diversity. They differ in size, density, luminosity, temperature. Stars also can change these parameters during the life cycle. Astronomers find stars of different ages and, according to these observations, can forecast their evolution. Most of them enlarge and lose density with time. For example, red supergiant Betelgeuse is close to finish and can explode any time. Its size surpasses the Sun by more than 1,000 times. Luminosity is more than hundreds of thousands times bigger. However, this star is colder than the Sun because of low density and huge surface. The main feature of Betelgeuse is its instability. Recently it remarkably faded, but now it is getting brighter again. In the last phase of life, lots of stars are similar to this behavior. Their size, temperature and glow are changing periodically. We named them Cepheids, and just Cepheids helped astronomers make a number of important discoveries. It turned out that their pulsation period is related to radiation power. Also, these stars are very bright and can be seen on great distance. And when astronomers see pulsating star and measure its period, they can calculate its luminosity, then compare it with visible brightness and estimate the distance to it. It is one of the ways of measuring distance to far galaxies. So what happens to stars when they die? Different types have different doom. The Sun is going to have the most inoffensive one. It will dump its upper layer and the remaining part will shrink to white dwarf. However, it will have already engulfed Earth during expansion. The formed white dwarf will be proximate to Earth's size, but because of high density it will almost have the mass of Sun. The first to talk about future of white dwarf was Indian astrophysicist Subramanian Chandrasekhar. He calculated that white dwarf can't have 1.5 mass of Sun, and if the mass grows at some point it will irresistibly shrink under gravity power, up to 0. And he was partially right. Now we can observe binary star systems where dwarf orbits so close to red giant that a stream of gas flows between them. This gas piles up into a layer on the white dwarf surface until it reaches a flash point and detonates in a runaway thermonuclear explosion. Astronomers call this burst a nova, but despite the huge release of energy, white dwarf remains intact. It loses a negligible part of the mass. After a while, the new portion of gas accumulates on white dwarf surface and nova happens again. It can happen periodically, once in several decades. Binary of two dwarfs will have even more intriguing destiny. When they approach and ultimately unite, such a star couldn't keep a balance. It will immediately collapse with a much more massive explosion. Either all substance will be scattered, or its core will be compressed to the neutron star. This explosion is called supernova, but collision of two dwarfs is quite a rare coincidence. Neutron stars can also appear after more massive star death. In that case, after supernova it will skip white dwarf stage and form much denser object. Neutron stars have really strong magnetic field and are extremely powerful sources of radio emission. Both white dwarfs and neutron stars strive to shrink under gravitational force, but degenerate gas pressure deters it. However, when dying star is more than 30 sun masses, its gravitation surpasses any barrier and star size strives to 0. This is the emergence of a black hole. I can talk about these mysterious objects in another video. Thank you for watching up to this moment. You can subscribe our Telegram channel and discuss whatever you want with us. And also don't forget to rate this video below. See you soon.